and welcome to this MEI M1 video where we're going to look at Newton's laws of motion. So for the specification we have to know and understand the meaning of these three laws and understand the term equation of motion, which is going to underpin the majority of the questions that we look at. We need to be able to form this equation of motion for a particle in one dimension or in two or three dimensions. And we need to be able to formulate and solve equations of motion for two separate particles that are connected to each other and find out various pieces of information about the situation. So let's have a look at Newton's laws. Newton's first law says that an object will remain at rest or it'll continue to move with a constant velocity unless it's acted upon by some external force. The second law, which is the one that we use the majority of the time in our calculations, is that the resultant force acting on a particle is equal to the product of the mass and the acceleration. The crucial word there is resultant force acting in any particular direction. So this equation will be used quite a few times. Newton's third law says that when an object exerts a force on another body, that body produces a force of equal magnitude onto the object, but in the opposite direction. To find an equation of motion for a particle, we therefore apply F equals ma in a chosen direction. And if there are two particles or more, you produce an equation of motion for each particle separately. Sometimes it's useful to look at the system as a whole rather than the two separate particles, and there's an example of that coming up later. So obviously a clear diagram showing the direction of all the forces is really important when we're solving these problems, because if you miss a force off your diagram, that's going to affect the accuracy of your calculations. So we'll start with quite a short question. That's the full question, so take a moment to read it through. And let's have a look at part 1. So we've got a particle that's got a mass of 5 kilograms. Initially the particle is at this particular position and its velocity at that time is 2 minus 3. So that's its initial velocity, which we tend to call u. After 4 seconds, the particle's got a velocity of 12.9. And the first thing we have to find out is the acceleration of the particle. Well, thinking back to our kinematics, we have an equation that we can use. So we can substitute in the 12.9 for the final velocity, 2 minus 3 for the initial. We don't know the acceleration, and the time is 4. Now you can put the 4 afterwards, but we tend to put numbers first, so 4a, 4a. Okay, so working that out, if I subtract the 2 minus 3 from the velocity vector, that'll give me 4a. So 12 minus 2, 10, 9 subtract minus 3, 12. So dividing by 4, that gives us 2.5 and 3 as the components of the acceleration. So for that part of the question we had a method mark for choosing a correct equation to work with and an accuracy mark for getting the correct answer. Calculate the position of the particle at the end of the 4 seconds. Now if you look back, we had a position that the particle was at initially, minus 1, 2. So I'm just going to jot that down. It's not starting at the origin, it's starting at a different place, so I'll come back to that in a moment. So we know that we have the initial velocity. We now know the acceleration, so a useful equation to work out the displacement from the starting point is this equation. S being the displacement from the start, and that's an important thing to remember. So u was 2 minus 3, that's being multiplied by t, which is 4, so I'll put that in front. And then we have a half multiplied by a, which we've just worked out, multiplied by t squared, which would be 16. So if we work out this vector, we're going to be doing 8 minus 6, minus 12 plus 20, 24. And so that works out to be 28, 12. Now that's the displacement during the 4 seconds, but the particle started from minus 1, 2. So from minus 1, 2, the particle has a displacement of 28, 12. So its new position will now be 27, 14. For the third part, we have to calculate the force acting on the particle. So for this part of the question, we'd have force is equal to mass multiplied by acceleration. So that would be the mass, if we look back, was 5. The acceleration, 2.53. So that would be 12.5, 15. So looking at the mark allocation, we would have a method mark for using a correct equation. Correctly substituting in the values gives an accuracy mark, and then working out the final position gave another accuracy mark. And then for part 3, correct method and getting the correct answer. Now we're going to have a look at one of the long 18-mark questions that come up on the second half of the paper now. So there's quite a few parts to this question. That's half of the question there on that slide. And this is the other half of the question. So it will be worth pausing the video on each of those 2 slides and having a good read through the details. So let's have a look at part 1. We've got a toy barge of mass 1.5 kilograms on a rough plane. So we know that there's going to be some friction involved. The plane's at an angle alpha to the horizontal. They've told us the value of sine alpha. Show the component of the weight of the barge down the slope is 4.2. Now we know that this angle here is also alpha, and so the component down the plane will be 1.5 g sine alpha. So that's 1.5 multiplied by 9.8, and then the value of sine alpha is 2/7. They've told us that in the question here. So if we work that out, it does work out to be 4.2 newtons. So we had a method mark and another mark there for explaining. Let's move on to the next part. So the barge is held in equilibrium by a force of 6.4 acting up and parallel to the plane. Determine the frictional force and state whether it's up or down the plane. Well, I'll add these onto my previous diagram. So 6.4 is up. You just have to make a choice. It doesn't matter if you get it wrong. The sign will just be different on your answer. So I'm going to assume the frictional force is down the plane like that. So if I resolve up the plane, parallel to the plane, we will have 6.4 acting up the plane, and then down the plane we'll have the friction and the component of the weight, which we've just worked out is 4.2. So the friction and the 4.2 component of the weight act down the plane, and we're in equilibrium. So rearranging, 6.4 minus 4.2 is equal to the friction, and that works out to be 2.2. That means that I chose the correct direction. If that had worked out to be minus 2.2, it means I chose the wrong direction, and so it's acting the opposite way to the way that I'd chosen. So we need to be really clear, state whether it acts up or down the plane. So it's 2.2 newtons down the plane. And in fact, in the mark scheme, you got a method mark for resolving. But to get the accuracy mark, you had to say also a direction. So if you only got 2.2, you would only get 1 mark unless you stated the direction as well. Okay, moving on to the next part of the question. The 6.4 force is removed and the barge is going to start sliding down the plane. Now, friction always opposes motion, so if it's sliding down the plane, friction would act in the opposite direction. And it's got an acceleration of 1.2. So we still have the mass, and we still have the resultant force. So because it's going down the plane, I'm going to resolve that way. And I'm going to use the equation F equals ma, Newton's second law. So I'm going to have 1.5 g sine alpha down the plane and friction acting the opposite way. They're the only two forces that have a component along the plane. So that's the resultant force. This F means resultant force. And that's equal to the mass, not the weight, the mass, 1.5 multiplied by the acceleration, which is 1.2. So, rearranging that, we will have 1.5 times g times sine alpha minus 1.5 times 1.2 will give us the friction. And so if we work that out, the friction works out to be 2.4 newtons. There were 4 marks for this part of the question. Applying Newton's second law gave a method mark. Getting this equation, perhaps with a sign error, got an accuracy mark. We got an accuracy mark there. And then the 4th mark, calculate the new frictional force on the barge. We need to say 2.4 newtons, and we need to say up the plane, so we need to give the direction, and the direction is important for getting that 4th mark. Next part, we have to work out how far the barge will travel while its speed increases from 0.8, that's the initial speed, to 2, which is the final speed. Now we know the acceleration is 1.2 and we want to know s. So, correct choice of equation would be v squared equals u squared plus 2as. And just substituting in the numbers, 2 squared equals 0.8 squared, and then we have 2 times 1.2 times s. So rearranging, we get 3.36 equals 2.4s. And so it's travelled a distance of 1.4 metres. 3 marks here, 1 mark for choosing a correct equation, an accuracy mark for putting the correct values in the correct places, and an accuracy mark for the final answer as well. Now the question gets a little bit more complicated because we have connected particles. So we've got the original barge, and then we've got a second barge as well. Now we're told quite a lot of forces, and the first part of this question is to draw the diagrams relating to these. So you may want to draw it on a separate picture. I'll just draw it on here just due to the amount of space we've got available. So 2 normal reactions, 2 weights. Now it says that we have a force of 10 newtons acting up the plane. That one's already been drawn on for us. Frictional force on barge B is 0.7. And the frictional force on barge A is now 2.3. I'll draw that here. But we also have a coupling in between them. And so that means we'd have a tension or a thrust acting in there. So I'll label that on now, although I may not need it until later in the question. So there would be two of those, one pulling backwards if it was tension on A, and one pulling forwards on B. So that's a diagram with all the forces on. And in fact, the first 2 marks out of this 7 marks was for getting all of those forces correct. So you got 1 mark if you got the frictions and the coupling forces, and then the second mark if you got it fully correct. So that's 2 of those 5 marks for the diagram. We now have to calculate the acceleration of the barges and clearly indicate its direction. Well, given that we don't know its direction, I'm going to make the assumption that it's going up the plane. And again, that might work out to be incorrect, but I'll just get a negative answer. Now, because we're not actually interested in working out this tension at this stage, I'm going to look at the system as a whole. So, going up the plane, which is the direction I've taken my acceleration, we have 10 going up the plane. We have 2 resistances, 2 frictions. There are 2 weights, 1.5 g, sine alpha is the component down the plane, and 2 g sine alpha for the other particle. Now there are 2 tensions or thrusts, but they're acting in opposite directions to each other, so they'll cancel each other out, and I don't need to include those in my calculations. So that gives us 3.5, the total mass, multiplied by the acceleration. We know sine alpha is 2/7, so substituting all of that in, this side works out to be minus 2.8. And so, actually, the acceleration works out to be minus 0.8. So, I'd taken my acceleration as being up the plane, but it's turned out to be negative. So, the acceleration is actually 0.8 meters per second, and it's down the plane. So, there were 3 more marks there. There was 1 mark for doing an equation of motion. We had a mark here, a B mark, for getting the correct overall mass and friction. So your total friction being 3, total mass being 3.5. And then 1 mark for the answer. Let's have a look at the final part of this question. We have to find the force in the coupling and state whether it's a tension or a thrust. So I'm going to look just at one of the particles, and I'm going to look at particle B. Now we know now that the acceleration is down the plane rather than up the plane. So when I do my resolving, I'll do it down the plane because we know that that's the correct direction. So if you imagine that barge A isn't there, and we just have a look at the forces acting on barge B, going down the plane, we would have the 0.7 and the 2g sine alpha. And going up the plane, we just have the tension. I'm assuming it's tension for now. That's the resultant force on that barge. And that barge has a mass of 2. So that would equal 2a. Rearranging this, 0.7 plus 2g sine alpha minus 2a, and a is 0.8, equals t. Notice how I'm taking a as 0.8 because I'm doing it down the plane, so I'm now going in the correct direction. Working that out gives us T is 4.7 newtons. Now because that's worked out to be positive, that means that it is a tension. The 4.7 is acting up the plane, so it's resisting the motion of barge B. If the T had worked out to be negative, that means it's acting down the plane, so it's pushing on barge B, so that would have been a thrust. But in this case, It is a tension of 4.7 newtons. So for the final part, we got a method mark for resolving for one of the objects, and we get an accuracy mark for correctly writing the answer. So that's a long 18-mark question, and it's worth practicing those because each individual section isn't too difficult, but it's really important to follow through the different parts and see which forces have been added and removed at each stage. Okay, let's have a look at one more question. So that's the full question. And let's have a look at the first part of it. So we've got these two boxes, P and Q. We have to draw a diagram. This is going to be my P. That's going to be my Q. So there's an upward force of 1,030 newtons on the box. And we know that this box P has got a mass of 75, so its weight is 75g. And there would also be a tension from the second box hanging downwards, and that would be the same as the tension upwards on Q. The only thing pulling down on Q is its weight. So we've drawn the two diagrams, and there's a mark for getting P correct and a mark for getting the forces on Q correct. Write down separate equations of motion for box P and box Q. Now, it says that the acceleration of the boxes is a meters per second upwards. So I tend to always resolve in the direction of motion. So I'm going to resolve upwards for both of those particles, and I'm going to use F equals ma. So if I do upwards for P, to start off with, we have 1,030 upwards and tension and weight downwards, and that would equal 75a. So I'm going to call that equation 1. If I do the same thing for Q, the tension acts upwards, weight downwards, and I'll call that equation 2. So we got a method mark for doing F equals ma for either one of those particles, and an accuracy mark for getting each one correct. So that's 3 marks in total for part 2. And then for part 3 we have to find the tension in the wire. Various ways to solve it. Doesn't really matter how you go about it. I'll multiply this second equation by 3. So I'll get 3t minus 75g equals 75a. So that's just multiplying that equation by 3. And the reason I'm doing that is because I can then put these two equations equal to each other. So I'll have 1,030 minus t minus 75g is equal to 3t minus 75g. So we've got a minus 75g on each side, they'll cancel. So I'll have 4t equals 1,030. T therefore works out to be 257.5 newtons. There's various ways to solve those simultaneous equations, so whichever way you're most comfortable with. So there's a method mark for solving simultaneous equations or showing that that was your intention, and an accuracy mark for getting the correct answer. So I hope you've found that useful looking at those problems, and I look forward to seeing you on one of the other videos for MEI M1.